we discuss application of HUCKEL molecular orbital theory to 1,3 butadiene system. Okay, application of HUCKEL molecular orbital theory to 1,3 butadiene. We all know that 1,3 butadiene, this is the structural formula of 1,3 butadiene. It has two alternate double bond, single bond, double bond. So these pi electrons, okay, they involve in conjugation. Okay, as per organic chemistry, we say that the electrons cloud and the pi electrons are freely moved from this end to that end. Now, as per HUCKEL molecular orbital theory, since 4 carbon atoms are there, 4 carbon atoms and each carbon has a p orbital, I have told you, you should assume the molecule is in the xy plane and these atomic orbitals are 2pz atomic orbital. Okay, 2pz atomic orbital and each orbital has one electron. Let me write like this. Each atomic orbital has one electron. So these 4 atomic orbitals combine and form 4 pi molecular orbitals. Isn't these p orbital, they combine together and form pi bonds or pi orbitals. So 4 2pz atomic orbitals, 4 2pz atomic orbitals, they combine and form 4 pi molecular orbitals. We get 4 pi molecular orbitals. Okay. Yes, how to find the energies of those 4 molecular orbitals? Yes, we have to use variation theorem. Okay. So, according to the variation technique, we can construct the secular determinant. So there are 4 atomic orbitals involving in this linear combination. Therefore, we should construct a determinant containing 4 rows and 4 columns. What are they? H11 minus E into S11, then H12 minus E into S12, then H13 minus E into S13, then H14 minus E into S14. Okay, this is first row. Similarly, we should write the other 4 rows. I'll just leave this as an exercise for you. You just try. Okay, and H31, ES31. Then we'll get H32, ES32, H33, ES33, H34, ES4 like that. Then H41, ES41. Then write everything. Then we get H44 minus ES44 equal to 0. We get a secular determinant like this. And when you use the HUCKEL's approximation, okay, what is HUCKEL's approximation? Just take them. So if I apply HUCKEL's approximation, what is that? HUCKEL approximation says, according to HUCKEL approximation, H11, H22, H33, H44. Okay, these are all integrals which will give you energy of an electron present in 2pz atomic orbital of carbon, which is nothing but equal to alpha. Okay, H11, H22, H33, H44 are nothing but integrals which give energy of an electron present in 2pz atomic orbital of carbon. Then, what about H12? H12 means adjacent carbon. H23, H34, right? H12, H23, H34, they are all adjacent carbon. So these integrals will give you the resonance integral whose value is beta. Other integrals like H13, right? H14, then H24, okay? H13, H14, H24, then 3, sorry, H13, H13 I already wrote, H31, this is the exact integral, same integral in a reversed manner. Okay, so all these integrals are equal to 0. Okay, they are all called, they are all not adjacent, they are not adjacent carbon, so the resonance integrals of these becomes equal to 0. Then S11, S22, S33, S44, these integrals are called normalization integral. The values of these integral equal to 1. And overlap integral S12, S13, S14, right, etc., etc. All these integrals are 0. I have discussed everything in the last class. Okay, if I substitute all these values in the secular determinant, and if you solve the determinant, you will get a polynomial equation. If you solve it, okay, you will get 4 solutions or 4 roots. Okay, you will get 4 roots, and if you substitute the 4 roots and find the energy, we get energies of the 4 pi molecular orbital. This is pi 1 bonding, pi bonding molecular orbital, pi 2, this is another pi bonding molecular orbital, pi 3 star, okay, this is anti-bonding molecular orbital, and pi 4 star, this is another anti-bonding molecular orbital. Okay, and what is the energy of this molecular orbital? After solving the determinant, and if I substitute, isn't E equal to alpha minus beta into x, correct? You should substitute the x values in this energy formula, and you will get the energies of the molecular orbitals. Okay, so we get the energies of 4 molecular orbitals. Let me give you the value directly. Okay, but this is a very simple one. You can easily construct, you can easily simplify the determinant, and you can simplify the polynomial equation also. You can solve it. It's a very simple one. I am going to give you the energy values directly. The lowest energy molecular orbital, energy of this is alpha plus 1.618 beta. Try to remember the value alpha plus 1.618 beta. Then alpha plus 0.618 beta. This is the energy of the next bonding, pi bonding molecular orbital. Then this is anti-bonding orbital, so alpha minus 0.618 beta. This is another anti-bonding, this is alpha minus 1.618 beta. Okay, these are the energies of the molecular orbitals. Now, what is the ground state configuration? Ground state configuration. Yes, 1,3-butadiene has 4 pi electron. Okay, there are 2 pi bonds. Each pi bond contains 2 electrons, so there are 4 pi electrons. Okay, 4 pi electrons are available, and we have to fill up these pi electrons in the pi molecular orbitals. Okay, for the ground state, listen, each molecular orbital can accommodate only 2 electrons, so place 2 electrons here and 2 electrons here. So we get the ground state configuration. So what is the ground state configuration? The lowest pi bonding molecular orbital has 2 electrons, and the next pi bonding molecular orbital has 2 electrons. Then the remaining molecular orbitals have 0 electrons. Okay, there is pi 3 star, which is 0 empty, pi 4 star is also empty. Okay, so in the ground state, this is the LUMO molecular orbital, lowest unoccupied molecular orbital, and this is HOMO molecular orbital, HOMO, called highest occupied molecular orbital. Okay, take note. So what is the pi electronic energy for the ground state? Pi electronic energy, which is nothing but, listen, in the ground state configuration, 2 electrons are present in the lowest energy molecular orbital, whose energy is alpha plus 1.618 beta, and another 2 electron present in the next higher level, which is alpha plus 0.618 beta, the energy of the next molecular orbital. Other orbitals are empty, so you need not consider that. Multiply this into 2, this into 2. So if we add them, you will get 4 alpha plus 4.472 beta. This is the pi electronic energy of 1,3 butadiene. Okay, take them. Now, what is the delocalization energy? Right here. Delocalization energy. Yeah, listen carefully. This is very, very important. Listen, in 1,3 butadiene, you know very well, we can write the resonance structures. So, pi electrons are delocalized. They are not localized on one carbon. Okay, we have 4 pi electrons. Don't think that each pi electron is localized on one carbon. No, the pi electrons are delocalized to all the 4 carbon atoms, all the molecular orbitals. So, what is the delocalization energy? Delocalization energy is nothing but pi electronic energy of 1,3 butadiene minus, listen, suppose if this pi system and this double bond, if this double bond and this double bond, if they do not undergo, if they are not involved in delocalization, listen carefully. Suppose if this double bond and this double bond, if they are not involved in delocalization, what would be the energy of those systems? So, this is one ethene unit, this is another ethene unit. If they do not interact, then what will be the total energy? The total energy is, okay, we have 2 ethene unit, so let me write 2 into, for each ethene unit, the energy is 2 alpha plus 2 beta. This is the energy of pi electronic energy of one ethene unit. And there are 2 ethene units, therefore, energy should be 2 into 2 alpha plus 2 beta. What is the pi electronic energy for 1,3 butadiene? Yes, which is equal to 4 alpha plus 4.472 beta. Then multiply this by minus 2, so we get minus 4 alpha minus 4 beta. Okay, plus 4 alpha minus 4 alpha cancel. 4.472 beta minus 4 beta, if you subtract, you get 0.472 beta. This is the delocalization energy of 1,3 butadiene. I have already told you beta value is always negative. So if you substitute the beta value and if you multiply, you will get some negative number. What does that negative number indicate? It indicates that much amount of energy is reduced if the 2 pi bonds involved in delocalization. Observe carefully. If the 2 pi bonds, okay, remains non-interacting, if they do not interact, then energy should be 4 alpha plus 4 beta. 2 into 2 alpha, so that is equal to 4 alpha plus 4 beta. Because of the interaction, okay, what happens? This much amount of energy is decreased. You all know when energy decreases, the stability of the system increases. So delocalization increases the stability of the system. Okay, take it. Now, what is the pi bonding energy? Pi bonding energy. Let me write like this. Pi bonding energy. This is pi electronic energy. Now what I am writing is pi bonding energy. Listen, what is pi bonding energy? It's very simple. It's nothing but pi electronic energy of the system minus, listen, pi electronic energy of the system minus, suppose if the p orbitals on each carbon atom, if they do not interact, if they do not involve in pi bond formation, then what will be the energy? What would be the energy for the system? Anyone?
4.
So, we should subtract 4 alpha so that you will get pi bonding energy. Okay, what is pi electronic energy for 1,3 butadiene? 4 alpha plus 4.472 beta minus 4 alpha. So, 4 alpha cancel. So, this 4.472 beta is nothing but pi electronic energy of 1,3 butadiene. Okay, this is pi electronic energy for 4 pi electrons. 1,3 butadiene has 4 pi electrons. For 4 pi electron, this is the pi electronic energy. Okay, take that. This is not pi electronic energy, this is actually pi bonding energy. 1,3 butadiene has 4 molecular orbitals. This is pi 1, this is pi 2, this is pi 3 star, and this is pi 4 star. There are 2 bonding molecular orbitals and 2 anti-bonding molecular orbitals. So listen, we have discussed about energy. Now I am going to discuss about the wave function. What is the molecular orbital wave function for the lowest energy molecular orbital? Okay. What is the wave function for the lowest energy molecular orbital? Okay. Yes, how to get that. Listen. I will write the wave function by symbol psi1. Psi1 equal to, listen carefully, for the in HUCKEL molecular orbital, remember, number of node in each molecular orbital, there may be 0 node or 1 node or 2 node. It depends upon the molecular orbital. Okay, number of node is equal to n minus 1. This is the formula we use. Okay, so if wave function is psi n, then it contains n minus 1 nodes. If the wave function is psi n, then it contains n minus 1 nodes. Okay, so what is the ground state wave function is represented as psi 1. Can anyone tell me how many nodes will be there?
0.
If there is no node, listen carefully. We have 4 atomic orbitals. 2p z orbital. This is 2p z orbital of carbon 1, 2p z orbital of carbon 2, 2p z carbon 3, 2p z orbital of carbon 4. I am going to combine the 4 atomic orbitals of carbon. Observe carefully. If there is no node, listen, first atomic orbital, some coefficient should be there. Some coefficient. Let me write this coefficient as C1. Let me write this coefficient as C2. This coefficient as C3. This coefficient as C4. It is our duty to find the coefficient, but I am not going to do that. I am going to give you some other information which is very useful for us. Since there is no node, psi1 means no node. No node. That means if the first atomic orbital has positive sign, the next should also positive. If there is same sign, no node. Next also positive. Next also positive. So all the signs remain same. Plus, 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 plus means, okay, all the p atomic orbitals, right, have same sign. So there is no node. What is the meaning? Let me draw and show you. So suppose this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. Suppose in carbon 1, in which we have a p orbital, carbon 2 has another p orbital, carbon 2 has a p orbital, and carbon 3 has a p orbital. Listen, don't worry about the size of the p orbital. Observe carefully. Size depends on the coefficient. Size of this atomic orbital, the atomic orbital size, okay, is decided by the coefficients. So right now we don't know what is C1, C2, C3. So don't worry about the coefficient. Just focus on the atomic orbital. Since the first atomic orbital is positive sign, I'll put plus in the upper lobe and minus in the lower lobe. Then second atomic orbital also has same sign, like the first one, okay, same sign. If there is same sign, then you should put plus above, minus. Don't change the sign. So third also, see, third one also has positive sign. So put plus, minus. Fourth also has positive sign. Now listen, all the upper lobes have positive sign, all the downward lobes have negative sign. Okay? This is the meaning. Now, we'll write the wave function for the next higher energy molecular orbital, which is psi 2. Psi 2 means there should be
only one node.
There should be one node, right? One node. Listen, always we should fix the node in a symmetrical manner. I have 4 carbon, correct? 4 carbon. Now I have one node. Where to place the one node? Since psi 2 has one node, you have to place that one node in the center of the molecule. Okay. So let me write that. So go C1 into Phi1 first molecular orbital, which is positive sign. Second molecular orbital also positive sign, which means there is no node between these two. Third molecular orbital, let me write C3 into Phi3. Okay, why? From plus to minus. If you move from plus to minus, sign is changing, which means there is a node between Phi2 and Phi3. Then since there is one node, yes, we have placed one node here. Between phi3 and phi4 there is no node. If phi3 has minus sign in front, phi4 supposed to have the same sign. So since this is negative, there is no node. Here positive, there is no node here. But when you move from here to here, okay, sign is changing, so there is one node available. Okay, how to represent this? Listen, let me write here. This one p orbital, another p orbital, another p orbital. Don't worry about the size of the p orbital, which is decided by the coefficient I told you already. Now, first atomic orbital positive, so put plus above, minus below. Second also positive, so plus above, minus below. For third, I have minus sign. Therefore, for the upper lobe put minus sign, for the lower lobe put plus sign. Then fourth one say again minus sign. That means upper lobe minus, lower lobe plus. So, listen, these two p orbitals have same sign. These two p orbitals have same sign. So, there is no node here. But when you come to second carbon and third carbon, see, sign is changing, which means there is a node in between. So, when there is a node, when a node is present between carbon 2 and carbon 3, so between 2 and 3, there should be a sign change. Okay. Between these, we have a node. Psi3 has two nodes, so we have to place the node between 1 and 2 and 3 and 4. So, plus 1 is plus, second one is minus, so there is a node. Then between 2 and 3, there is no node, so you should keep the sign as such. Then between 3 and 4, we have one node. If this is minus, this should be. If this is minus, this should be plus, which means there is a node between carbon 3 and carbon 4. Is this clear to all? You tried to find out Psi4. Yes. So this is the molecular orbital scheme, right, for pi 4 star molecular orbital. Okay, wave function. Right. Now I'll give a question. You try to answer it. In the case of allylic system, right, allyl cation or allyl radical or allyl anion, whatever it is, we get three molecular orbitals. Okay, this is Psi1, this is Psi2, this is Psi3. Psi1, Psi2, Psi3. Now I will leave it to you. Okay, you try to find out how the wave functions exist. Listen. No, you need not write the coefficients. Okay, you need not find the coefficient. You just write the coefficient as C1, C2, C3. Okay, yes, do it. Tell me.
Plus P1 plus
yes,
P2
1 second.
plus
Yes,
P2, sir.
yes, you are right. C1 plus C2 Phi2 plus C3 Phi3, because Psi1 means, okay, zero
No
node.
node, sir.
Zero node. No node, okay. Zero node means all the signs supposed to be same. Plus, plus, plus. Okay, good. Very good. And how the molecular orbital look like? Is it how the atomic orbital combine? Let me write here. So, don't worry about the size of the orbital. I am going to focus only on the sign. If the first orbital has plus above, minus below, second one also has plus above, minus below, third one also has plus above, minus below. Okay, so this is the molecular orbital, the orientation of p orbital in the formation of molecular orbital for the ground state for Psi1. Okay. Yes. What about Psi2? Yes. Anyone? So Psi2 has one node. So how to write? Listen. One node means we have three carbon. Listen carefully. In the case of linear molecule, if there are odd number of carbon, 1, 2, 3, if there are odd number of carbon, okay, listen, sometime node present on the carbon itself. So now I have one node here, that one node present on the middle carbon. Okay, therefore, see the coefficient C1 into Phi1. Okay, second becomes 0 because second orbital do not contribute because node is there. Then third one, C3, third one is minus C3 Phi3. Why minus? This is plus because it's 0 anyway, leave it. Why third one is minus?
Node, sir.
We have a node here. So listen carefully, let me draw the structure. this is carbon 2, this is carbon 3. Now this is plus minus. Since this is the node, the node is present on carbon 2 itself. Since there is a node here, so when you move from this to this, sign should change. So if this is plus, this should be minus, and this should be plus. So for carbon 1, if it is plus C1F1, for carbon 3, we should get minus C3F3. Okay, this is the wave function for side 2. What about side 3? So side 3 has 2 nodes, so it is very easy. You should place the 2 nodes between the carbon. Okay, so C1F1 plus minus C2F2, then plus C3F3. When sign changes plus to minus, that means there is a loop. There is a node. So between carbon 1 and carbon 2, we have a node. Then here also see, sign changes minus to plus. When there is a sign change, there is a node. So I have a node here, I have another node here. So there are 2 nodes. Okay. This question appeared in CSIR Net December 2023. The question is this: the following molecular orbital corresponds to HOMO pentadienyl cation, HOMO of pentadienyl anion, LUMO of pentadienyl cation, LUMO of pentadienyl anion. Listen, here instead of sign, they have given some shaded lobe. This is shaded and this is unshaded. Similarly, this is shaded lobe and this is unshaded. Instead of plus minus, sometimes they will give like this. And here this is shaded portion and this is shaded portion. Okay, and this is another carbon. I have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Okay, because it is penta system, that should be 5 carbon. Now, how many nodes are there? Can anyone tell me? Since there is one node, so this is a node actually. Node. So we have one node. One node means the wave function should be side 2. So it should be a second molecular orbital. Okay, listen. There are 5 molecular orbitals because 5 carbon atoms are there. So there are 5 molecular orbitals. Okay, this is psi 1, this is psi 2, this is psi 3, this is psi 4, and this is psi 5. So now, listen, if it is cation, suppose. If it is cation, it has only 4 electrons. Let me write here, listen. If it is a cation, let me put just plus symbol. Plus means cation. If it is a cation, there should be only 4 pi electron. So I place 2 here and 2 here. So, listen, this is the highest occupied, correct? In the case of cation, this is highest occupied molecular orbital. So side 2 is nothing but highest occupied molecular orbital. If it is a cation. If it is an anion, what will happen? If it is an anion contains 6 electrons. So we place 2 here, 2 here, 2 here. In the case of anion, side 2 is not a HOMO. Side 3 is actually HOMO and psi 4 is the LUMO. Okay, psi 4 is LUMO. Are you able to understand this? In the case of cation, side 2 is HOMO, side 3 is LUMO. Now I have seen the molecular orbital has one node. If it is one node, then it should be side 2. If it is side 2, okay, in the case of cation, it is HOMO. In the case of anion, it is neither HOMO nor LUMO. So it cannot be an anion first of all. It cannot be an anion. Okay, it should be a cation. Whether it is HOMO of pentadienyl cation or LUMO. It cannot be anion. Keep that in mind. It cannot be anion because side 2 is, in the case of anion, side 2 is neither HOMO nor LUMO. So it should be only cation. In cation, I have HOMO and LUMO cation. Whether it is HOMO or LUMO?
HOMO, sir.
It should be HOMO. So the correct option is 1. Take note. Correct answer for this question is option 1. Okay. Question. Let's try to answer this question. Find the ground state pi electronic energy of this molecule. Find the ground state pi electronic energy of this molecule. Yes.
1, 3.
Yeah. So this given system, it is similar to 1,3 butadiene. Okay. You need not worry about the sigma bonds. Okay, HUCKEL theory does not consider sigma bonds. It considers only pi bond and pi electrons. Okay, since it is similar to 1,3-butadiene, so pi electronic energy is equal to 4 alpha plus 4.472 beta. Listen, everyone try to remember this value for 1,3-butadiene, which is very, very important. Okay, right now we will see the application of HUCKEL molecular orbital treatment for cyclic polenes. Cyclic polenes. Okay. Right. So on the cyclic polyene, first I will take the simplest cyclic system, that is cyclopropyl system. I will place a double bond. So it is cyclopropene. Listen, you can take a cation or a radical or an anion. Okay. It may be cyclopropenyl cation or cyclopropenyl radical or cyclopropenyl anion. Whatever it is, molecular orbital remains same. Only the number of electrons will differ. Okay. Now listen, if a system is given like this, what we should do? The first step is draw the corresponding Frost cycle. Okay. First draw the Frost cycle for the compound. What is Frost cycle? Draw a circle and place a line at the center. This is called the barycenter, or I will put alpha. This is along this line energy is alpha. Meaning, if the p orbital do not involve in bonding, or if the electron in p orbital do not involve in bonding, the energy is alpha. Below this we have bonding molecular orbital, and above this we have anti-bonding molecular orbital. Now what to do? If the cyclic system is given, draw the cyclic system in this circle in such a manner that one carbon should be at the bottom. Always draw the cyclic system in such a manner that one carbon should be at the bottom. So it is cyclopropane, so I will keep one carbon here. So remaining 2 carbon will be like this. We have to draw the cyclic system in this way. So I have a molecular orbital here, and we have 2 molecular orbitals, one here and one here. So the corresponding energy, let me draw energy. I have a molecular orbital and I have 2 molecular orbitals which are degenerate. Okay, this is the cyclopropenyl system. Right? And remember, always the energy of the bottom carbon, whatever system you take, whatever cyclic system you take, always the energy of the bottom carbon, bottom molecular orbital should be alpha plus 2 beta. Always. So energy of this molecular orbital is alpha plus 2 beta. Okay. Now, what is the energy of these two? Suppose if I have a molecular orbital exactly opposite to this, then the energy of that should be alpha minus 2 beta. But there is no molecular orbital now. I have molecular orbital below this, and their energies are alpha minus beta. This is alpha minus beta. This is also alpha minus beta because they are degenerate. So they have same energy, alpha minus beta. Okay, take it. Now listen carefully. This is the molecular orbital. Now we will find out the energy. First I will take cyclopropyl cation. I will take the first system. A cyclopropyl cation will take. In the case of cyclopropyl cation, how many pi electrons are there? How many pi electrons? Yes.
2 pi electrons.
We have only 2 pi electrons. Okay, 2 pi electrons. Right? Number of pi electrons is 2. So now I am going to place the 2 electrons, okay, in this molecular orbital. Listen, let me draw here. We have a lower energy molecular orbital, and this is bonding. This is bonding, and these 2 are above the center line. They are anti-bonding. I have only 2 electrons, and you know very well each molecular orbital can accommodate 2. What is the energy of this molecular orbital? Alpha plus 2 beta. And these molecular orbitals have energy alpha minus beta, but there is no electrons, we need not worry. So what is the pi electronic energy of the ground state? Pi electronic energy of the ground state is equal to, since both electrons are present, yes, for each electron energy is alpha plus 2 beta. So I have 2, so 2 into alpha plus 2 beta, which is equal to 2 alpha plus 4 beta. This is the pi electronic energy of cyclopropenyl cation. Okay, then what is the next step? It also undergo delocalization, correct? I can shift this pi bond here If I shift the pi bond here, I'll get carbocation here. I can write many possible resonance structures. So delocalization is there. What is the delocalization energy? Delocalization energy. Delocalization energy is nothing but pi electronic energy minus, see, I have one ethene-like system, right? Ethene-like system. One ethene-like. So energy of ethene-like system is 2 alpha plus 2 beta. Right? So what we get? Pi electronic energy is 2 alpha plus 4 beta minus 2 alpha minus 2 beta. So plus 2 alpha minus 2 alpha cancel. 4 beta minus 2 beta will give you 2 beta. So delocalization energy is 2 beta. Beta is negative. So what does it imply? Try this for cyclopropenyl radical. So now we have the bonding molecular orbital whose energy is alpha plus 2 beta, and we have two degenerate anti-bonding molecular orbital whose energy is alpha minus beta. Now how many pi electrons are there? This pi band has 2, and we have an odd electron that is also involving in resonance. So you should consider that electron also as pi electron. So there are totally 3 pi electrons available. Now if I fill up the electrons here, place 2 electrons in the lower energy molecular orbital, remaining 1 should be placed here or here, it's up to you. Okay, now what is the pi electronic energy? Pi electronic energy equal to 2 electrons have energy alpha plus 2 beta, and 1 electron has energy alpha minus beta. So what we get is 2 alpha plus 4 beta, here plus alpha minus beta. So 2 alpha plus alpha will give you 3 alpha, 4 beta minus beta will give you 3 beta. 3 alpha plus 3 beta is the pi electronic energy of cyclopropenyl radical. Now, what is the delocalization energy? Delocalization energy is pi electronic energy minus, observe this carefully, this system has one ethene unit and we have one odd electron. The system has one ethene unit and we have an odd electron. For ethene, energy is 2 alpha plus 2 beta. For ethene, energy is 2 alpha plus 2 beta. If this odd electron is not involved in bonding, suppose, if the odd electron is not involved in resonance or delocalization, what is the energy of that electron? Alpha. Correct? Yes. So pi electronic energy is 3 alpha plus 3 beta minus 2 alpha plus alpha is 3 alpha, so I will get minus 3 alpha minus 2 beta. Plus 3 alpha minus 3 alpha cancel. 3 beta minus 2 beta will give me beta. This is the delocalization energy of cyclopropenyl radical. Okay. Exercise. Okay. So you try to find out what is the pi electronic energy and delocalization energy of cyclopropenyl anion. Okay. So you take it as homework. Yes, we can also find pi bonding energy. Nothing wrong there. Pi bonding energy. Yes, what is pi bonding energy? It is nothing but pi electronic energy minus, suppose if all the p orbitals, if they do not involve in bonding, what will be the total energy?
3 alpha.
3 alpha, correct. So I have pi electronic energy which is 3 alpha plus 3 beta minus 3 alpha, so I will get 3 beta. 3 beta is the pi bonding energy for 3 electrons. Okay. So the next system we are going to consider is cyclobutene-like system. So let me take 1,3 cyclo butadiene. 1, 2, 3. 1,3 cyclobutadiene. Since it is cyclic system and we have conjugated pi electrons, we can use HUCKEL molecular theory. What is the first step? Draw the frost circle or frost cycle. Put a line at the center and the energy of this line is alpha. If any p electron, if it is not involved in bonding, the energy is alpha. Below this we have bonding and above this we have anti-bonding. Now listen, we have to draw this cyclobutene system in this circle such that you should keep one carbon at the bottom. So I'll place one carbon here. Since it is square, so we should draw a perfect square. See this. This is how we draw the perfect square. Now, see, I have a molecular orbital here. I have a molecular, so let me draw like this. I have a molecular orbital. This is bonding. And we have two molecular orbitals, right? Exactly at the center. Right? We call these molecular orbitals as non-bonding molecular orbital. They are not involved in bonding. And we have an anti-bonding molecular orbital here. What is the energy of this one? Can anyone tell me? What is the energy of the bottom?
Alpha plus 2 beta.
Always. Yes, you are right. Always alpha plus 2 beta. What is the bottom of this top?
Alpha minus
Alpha minus 2 beta.
Alpha minus 2 beta. Exactly opposite alpha minus 2 beta. What about the energy of these two?
alpha.
Alpha plus.
Yeah,
Alpha minus beta.
they exist on the line. Therefore, their energies are alpha. Am I right? They are non-bonding. They are not involved in bonding. That's the meaning. Okay. Now listen. How many pi electrons are there here in this case? How many pi electrons?
4 pi electrons.
There are 4 pi electrons. So, if I place 2 electrons here and we have 2 more electrons, place 1 here, 1 here. This is the electronic arrangement. Now tell me, what is the pi electronic energy of this system? Yes. What is the pi electronic energy? 2 electrons have this much energy. So, 2 into alpha plus 2 beta. And these 2 electrons have energy alpha. So, we have 2 electrons. They have energy alpha. So, what we get is here 2 alpha, here 2 alpha. So, we'll get 4 alpha plus 4 beta. 4 alpha, 4 beta. Yes, this is the pi electronic energy of 1,3 cyclobutadiene. Now, what is the delocalization energy? Yes, I have alternate double bond. See, double bond, single bond, double bond. Since we have alternate double bond, conjugation is possible. Resonance is possible. Okay, so what's the delocalization energy? Delocalization energy, you know very well, is nothing but pi electronic energy minus. Suppose if this ethene unit and if this ethene unit, if they do not involve in resonance or conjugation or delocalization, if they do not involve, what would be the energy, expected energy? 2 into
2 alpha plus 2 beta.
Yeah, this is energy of one ethene unit. There are 2 ethene units, so 2 into this. So, pi electronic energy is 4 alpha plus 4 beta. If I multiply this by 2 here, I will get 4 alpha and 4 beta. 4 alpha cancel, 4 beta cancel. I am getting delocalization is just 0. Yes, this system is anti-aromatic system. So, the cyclopentane system, supposed to pentadiene system, supposed to appear like this in process. And the energy of this, so I have one molecular orbital here, and these 2 molecular orbitals are bonding, degenerate. These 2 molecular orbitals are anti-bonding, degenerate. So, in cyclopentadiene system, I have a bonding molecular orbital and another bonding molecular orbital which are degenerate, 2 bonding molecular orbitals which are degenerate. Then we have barycenter here, and above this we have 2 molecular orbitals which are also degenerate. They are called anti-bonding molecular orbital. And the energy of the bottommost, you know very well, alpha plus. Energy of the bottommost is always alpha plus 2 beta. And listen, these 2 molecular orbitals are below alpha, so their energy is alpha plus beta. These 2 are above alpha, they are alpha minus beta.
Alpha minus beta.
But listen carefully. Listen, they are not actually equal. Okay, here I have 3, here I have 2, they are not equal. So you will never get beta, you will get some number which is 1.618 beta. Okay. Let me write here once again. So these are the energy values. This is alpha plus 1.618 beta, these 2 degenerate molecular orbitals. And these 2 molecular orbitals have energy alpha minus 1.618 beta. Now, let me take one example. Say I'll take cyclopentadienyl anion. I will take anion. Cyclopentadienyl anion. How many pi electrons are there? Number of pi electrons?
6 pi electrons.
Yeah, there are 6 pi electrons. Okay. So now we have to fill up. We have 1 bonding molecular orbital and 2 degenerate bonding molecular orbital. This is the barycenter, and we have 2 anti-bonding molecular orbital. Energy of this is alpha plus 2 beta. Energy of this is alpha plus 1.618 beta. Energy of this is alpha minus 1.618 beta. Now I have 6 electrons. Each molecular orbital can accommodate 2. So place 2 here, 2 here, 2 here. Listen carefully. All the electrons are present in only bonding or anti-bonding?
Bonding molecular orbital.
All the electrons are in bonding molecular orbital, so it should be aromatic. Yes, cyclopentadienyl anion is aromatic species. Okay, you all know that. Okay, take note. How to find the pi electronic energy? We have 2 electrons having this energy, 2 into alpha plus 2 beta. And we have 4 electrons, these 2 are degenerate. So there are 4 electrons, they have energy alpha plus 1.618 beta. So this is 2 alpha, this is 4 alpha, you will get 6 alpha. And here we will get 4 beta. And here if you multiply this by 4, you will get some value. Yes,
10.472 beta.
10.472 beta. Okay, this is the pi electronic energy of cyclopentadienyl anion. Cyclopentadienyl anion. Okay, now what is the delocalization energy? Which is nothing but pi electronic energy minus, I have 2 ethene-like system. So 2 into 2 alpha plus 2 beta plus I have 2 electrons present in p orbital. Okay, if 1 electron present in p orbital, energy is alpha. Now we have 2 electrons, so 2 alpha. Okay, so here I have 6 alpha plus 10.472 beta. Here, see 2 into 2, 2 alpha, and here I have 2 alpha, so I have 4 alpha. So minus 4, I'm very sorry. This is 4 alpha, here 2 alpha will be 6 alpha. 6 alpha, then 4 beta, minus 4 beta. 6 alpha cancel. 10.472 minus 4, if I subtract, we'll get 6.472 beta. Am I right? This is the delocalization energy. Am I right? Check it. Now, so we'll move on to the next system, that is benzene system. Okay. So, benzene, it is perfect hexagonal molecule. Right? Draw the benzene in frost cycle. So this is the center, whose energy is alpha. Now you should draw hexagon inside this circle such that you should keep 1 carbon at the bottom. So place 1 carbon here, and since it is hexagon, okay, we should keep another carbon here, 2 carbon here, 2 carbon here in a symmetrical manner. So now connect all this, all the adjacent carbon. We get an hexagon like this. Okay, can anyone tell me what is the energy of this? Let me draw the energy of molecular orbital. Okay, we have the center, so this is alpha. Now I have 3 molecular orbital which are bonding and 3 molecular orbital which are antibody. They are symmetrically located. So what is the energy of this? Can anyone tell me what is the energy of this?
Alpha plus
Alpha plus 2 beta. What is the energy of the topmost?
Alpha minus
Alpha minus 2 beta. And these 2 orbital, they are degenerate, they have energy alpha plus beta. And these 2 orbital which are degenerate, which has energy alpha minus beta. Very good. How many pi electrons are there? Number of pi electrons?
6.
6. So place the 6 electrons here. 2 here, 2 here, 2 here. So all the molecular orbitals, all the bonding molecular orbitals are filled, completely filled. So it should be aromatic. And what is the pi electronic energy? Pi electronic energy equal to 2 electrons have energy alpha plus 2 beta, and the 4 electrons have energy alpha plus beta. So we get, here we have 2 alpha, 4 alpha, so 6 alpha. Here we have 4 beta plus 4 beta, I have 8 beta.
8 beta.
This is the pi electronic energy of benzene. Take note. Find the next step, find the delocalization energy of benzene. Yes, how to do that? Energy is nothing but pi electronic energy minus. Yes, there are 3 ethenic system, right? 3 ethene like system. So 3 into, for each ethene, the energy is 2 alpha plus 2 beta. So this is 6 alpha plus 8 beta, and this is 6 alpha plus minus 6 beta. If I multiply by minus inside, 6 alpha cancel, 8 beta minus 6 beta, I'll get 2 beta. Okay?
2 beta.
Yes, what does this question appeared in CSIR NET June 2011 examination. The energy levels for cyclobutadiene, observe carefully, cyclobutadiene are alpha plus 2 beta, alpha, and alpha minus 2 beta. The delocalization energy in this molecule is, you know very well, cyclobutadiene system, if you draw the Frost cycle, yes, this diagram will appear like this. And this is the center. Right? These two molecular orbitals, they are non-bonding. So let me draw here. This is bonding. So we have a bonding molecular orbital whose energy is alpha plus 2 beta. And we have an exactly anti-bonding molecular orbital, exactly opposite. So energy is alpha minus 2 beta. And we have two molecular orbitals which are non-bonding because they are exactly lies right on the center line. So whose energy is alpha. And cyclobutadiene has 4 pi electrons. If I place 2 here and 1 here, I'll get 4. What is the pi electronic energy? Pi electronic energy equal to, these 2 electrons have energy 2 alpha plus 2 beta, so 2 into alpha plus 2 beta, and these 2 electrons have energy alpha. So we get 2 alpha plus 2 alpha, we get 4 alpha plus 4 beta. This is pi electronic energy of cyclobutadiene. See, cyclobutadiene, whose pi electronic energy, ground state pi electronic energy is 4 alpha plus 4 beta. What is the delocalization energy? That's the question. Delocalization energy is nothing but pi electronic energy minus, see this 1,3 cyclobutadiene has 2 ethene like system, 2 ethene unit. But if they do not interact, the total energy of the ethenic unit should be 2 into, there are 2 ethenic units, so 2 into 2 alpha plus 2 beta. This is 4 alpha plus 4 beta. If you multiply this by minus 2, I will get minus 4 alpha and minus 4 beta. See, plus 4 alpha minus 4 alpha cancel, plus 4 beta minus 4 beta cancel. So I am getting the answer as 0. Delocalization energy of cyclobutadiene is 0. So correct option is A. Okay, take it. This question appeared in June 2012. Using HUCKEL molecular orbital approximation, the 2 roots of circular equations of ethene are. What are the 2 roots? Okay. Yes. Listen, if you solve the circular equation, right, and you will get 2 energy values finally. Okay, one is alpha plus beta, the other one is alpha minus. These are called roots. Okay, so the correct option for this question is option C. Those who have some idea about HUCKEL molecular orbital theory of ethene, they can directly answer this question. Okay, yeah, take it. This question appeared in December 2013. The question is this: the energy for a single electron excitation in cyclopropenium cation in HUCKEL theory. Cyclopropenium cation in HUCKEL theory. Single electron excitation. How much energy is required? So a simple one. Cyclopropenium
1
cation.
beta, sir.
Yes.
1 beta.
Cyclopropenium cation. Yes, your answer is correct. Cyclopropenium cation. If you draw the Frost cycle and if you find the molecular orbital energies, I have told you, one molecular orbital have one is bonding, the other 2 are anti-bonding. Bonding molecular orbital energy is alpha plus 2 beta, and these 2 are alpha minus beta. Okay. Now, in cyclopropenium cation, we have only 2 pi electrons. The 2 pi electrons exist in this bonding molecular orbital. Now, for a single electron excitation, so if excitation takes place, listen, if excitation takes place, what will happen? Single electron excitation, one electron will move from alpha plus 2 beta, this molecular orbital, to higher energy molecular orbital. This is called single electron excitation. What is the energy required for this? This is very simple. Energy of the higher orbital, okay, excitation energy, let me write here, excitation energy required for excitation. It is the energy of the higher molecular orbital, which is alpha minus beta, okay, and energy of the lower molecular orbital, which is alpha plus 2 beta, right? So if we subtract, what will I get?
Betas.
So the correct answer for this question is option 3. 3 beta energy is required. Okay, it appeared in 2018 December. One of the HUCKEL molecular orbital is given here. The energy of this orbital in terms of the Coulomb and resonance integral is. The first step is find the number of node. So here I have positive sign, here positive sign. So there is no node between carbon 1 and carbon 2, no node. Then here carbon 2 to carbon 3, this is plus, this is minus. So there is a node. We have a node here. Then carbon 3 to carbon 4, minus, minus, same sign. Same sign means no node. So how many nodes are there? How many nodes? One node. So this molecular orbital, okay, the given molecular orbital, yes, it has one node. One node means the wave function is supposed to be psi 2. For 1,3-butadiene, you know, for 1,3-butadiene, right? The energy of the lowest molecular orbital, which is psi 1, the energy of this molecular orbital is alpha plus 1.618 beta, you know very well. And the second molecular orbital, psi 2, whose energy is alpha plus 0.618 beta. And third molecular orbital, psi 3, whose energy is E3 equal to alpha minus 0.618 beta. And the fourth one, psi 4, whose energy E4 equal to alpha minus 1.618 beta. Now, they are asking the energy of this orbital, this molecular orbital, which has one node. One node means it should be psi 2. For this orbital, energy is alpha plus 0.618 beta. So, alpha plus 0.6, 0.618, you can write as 62, correct? Roughly. So, the correct option for this question is option 2, right? This question appeared in 2019 June. The highest energy pi molecular orbital for the allylic system, allyl cation or allyl anion or allyl radical, whatever it is. What is the highest energy pi molecular orbital?
2 nodes.
Yeah. Since it is allylic system, there are 3 carbon atoms. So 3 p orbitals are involving. Okay. 3 p orbitals, so you will get 3 molecular orbitals. Right? Psi 1, psi 2, psi 3. Highest energy molecular orbital is psi 3. Psi 3, therefore there should be 2 nodes. Okay. So between carbon 1 and carbon 2, there should be a node. Right? There should be a node. So if we move from here to here, in option 3, I have plus here and minus here. So there is one node. Then 2 to 3, if you move from second carbon to third carbon, again sign is changing. So I have one more node. So the third option has 2 nodes. In first option, no node. In second option, we have one node which is present at the middle carbon, correct? We have one node which is present at the middle carbon. That's why the psi 2 is missing, chi2 is missing. And here, see, I have plus to minus one node, minus to minus no node. I have one node but which is not present symmetrically. So this is not at all possible. So the correct option for this question is option 3. Right?